Hello, welcome to 229. This is lecture 9. We're going to talk about a couple of unsupervised algorithms. So most of the focus for this week is going to be about algorithms where we don't actually have any labels, but we still want to do a bunch of machine learning. And as we talked about before, this direction of using weaker labels or unlabeled data and understanding structure has uncorked a whole bunch of applications in machine learning over time. We're going to see two of the most common unsupervised algorithms, or popular, which are very closely related, which are k-means and the Gaussian mixture model. Okay? And these are just kind of the canonical set. That's why we're going to go over them. Now, hopefully, as we go through these two, we're going to learn this idea of expectation maximization, this EM algorithm. I will tell you, EM in general is kind of an algorithm you run not as a last resort, but you run it typically because you have only a very weak knowledge of the structure. Often, and for some of these problems, you can find another method to solve them if you know more about it or are willing to make stronger assumptions. But we're going to see it because it's like a classical algorithm. Like one of my graduate students was just writing for his submission next week. He's going to write what's called an elbow. If you don't know what an elbow is, you'll learn soon, for his particular diffusion style estimator. Okay? Now, we're going to talk about k-means and its probabilistic analog GMM. K-means is going to be hopefully intuitive to think about. It's going to be kind of ad hoc though, in the way we think about it. And then we'll see Gaussian mixture models, which are a softer version of this kind of clustering. And those are going to be kind of the duality. Now, the techniques and ideas here are pretty useful on their own. As I mentioned to you, unsupervised algorithms have had a renaissance over the last 10 years. But more than anything, the reason pedagogically I like this section and the section that we're going into is it forces you to wrestle with some pretty basic questions in machine learning, right? What are we modeling? How are we putting structure into our models? What are we pulling out of it? And so we'll get a taste of that. And that's really the pedagogical goal. Like the algorithms, you could just look up in 5 minutes. But why we think about these algorithms, why we pick them, that's what I want you thinking about during this lecture and next. All right. So here is kind of the picture that should go in your head. Okay. Very, very basic kind of picture. Oh, I'll get this guy going. So you have some axis. In supervised learning, how did it work? Well, we had some points, here, and then maybe we had some, positive points there, and then maybe we had some negative characters over here. And our goal was draw some line that separated them. Okay? So this is the supervised world is what I'm talking about. Okay? And here we had these labels. The positive and the negative were our labels. All right. Now in the unsupervised, we're going to get rid of the labels. So here's the same data set. Okay? Roughly speaking. I should have drawn them to be isomorphic. Okay? Just me being a terrible drawer. There will be a lot of drawing in this lecture because I used to give this on the whiteboard and I like doing it. I am not sure that it's super effective. So we'll see. I don't know. This is unsupervised. And there are no labels. Okay? Now, that bit of structure, that label, the fact that we had pluses and minuses here, let us actually give a pretty strong characterization of what we were after, right? We wanted something that would exactly separate the sets. There was kind of one canonical version of what we were after. In this unsupervised regime, it's not clear what a model means. We talked about it a little bit in GDA, where remember in GDA you had two different labels and you tried to learn a model of the labels. Here somehow we kind of want to learn a model that describes the data set, the clusters that are inside it, some qualitative structure of it that could kind of help us classify it. Okay? And the point that I'm making is that's a pretty unstructured problem. And so we're going to have to make accept weaker guarantees. We're not going to be able to say things about like the perfect line that does it. So we're going to have to think a lot about modeling. And we're going to have to make potentially stronger assumptions to say, oh, our data is generated by this process. And so we could potentially recover it, right? If we saw it in some way. And the assumptions we have to make there are just intuitively going to be a lot stronger. Okay? The unsupervised learning here is going to be harder than the supervised, and so we'll make stronger assumptions and accept weaker guarantees. Okay? All right. So far, so good. All right. Please. Yeah, so it's possible that some of the things, in fact, the algorithm that we're going to point to today, actually finding the optimum will be harder. I meant it in a more qualitative sense. So harder in the fact that actually getting the optimum for k-means will be NP hard. And so in a formal sense, it is actually more challenging computationally. It doesn't mean that every instance of how we solve it is going to take more time. That's not the case. But intuitively, it will be more challenging. That's what I want to get across to you. Because we've dropped some assumptions, right? We've dropped some very important structure. We don't know the positive and the negative class. We don't know the class labels. Okay? Good question. Awesome. Are there others? All right. Now, by the way, I should also say, if you really miss my hand drawings, a better version of them should be online in the notes so you can actually see what I'm intending to draw. And then you can laugh about like what's in the notes and then what shows up when I scribble it here. Okay? So what we're going to do today, we are going to talk about the k-means algorithm, which will be hopefully intuitive. It should be, if I do my job right, you'll kind of understand how it works. It may feel a little ad hoc. It may feel a little bit heuristic, but we'll see. We'll talk about a probabilistic method for the Gaussian mixture models, which we talked about will be this nice relaxation. And then I probably, if we have time, we'll talk about Jensen's inequality and pictures. By show of hands, who knows Jensen's inequality? Okay, about half. All right, fantastic. You'll see it in pictures in a nice, hopefully simple way that it will click in your head. The reason those pictures are important is that turns out to be the core of this algorithm, EM, that we're going to see in the last half of the lecture and into the next lecture. Okay, that's our structure. Okay, so let's get to k-means. All right, so in k-means, we're going to have this, k equals 2. So what are we given in this setup? So here we have some data. Okay, so this is what we're given. There's our data. And just as we talked about before, there are some points. And I've drawn the points here. Now what the k equals 2 is talking for, that's what this k is, says that I want 2 clusters. So you could ask, why 2 clusters? Why not 4 clusters? That'll turn out to be a modeling parameter. Okay? For now, just imagine that 2 is the thing that we're after. What we want to do somehow is, and I would say, kind of the best 2 clusters, and we'll talk about what best means in a second. Maybe these characters are a nice cluster, and these characters over here are a nice cluster, okay? All right? Now, you can think about what that means, that these points are a nice cluster. One way to do it, one thing that we want to do it is, we're going to be given these integer k and these points. This is x1, right? For example, this is say x1. This is x2. And we're going to assign each of them mathematically to one of the k clusters. Okay, so that's what this ci equals j is going to mean. It says point I goes to cluster j. So all these points here are going to cluster 1, and all these points here are going to cluster 2. So that's what we are given in the do. We're given the points without any labels, and our job is to come up with this assignment, which I've drawn and scribbled with my blue and my kind of pinkish orangish color on there. But really mathematically, it's going to do here. And I don't actually know. See, it is, so I'll make C2 should be over here. So I'm going to change the label. I'll make this guy C4 to align with this. And I'll move X2 over here to align with this. Clear enough what the mapping means? Okay, cool. All right, so how do we find these clusters? We're going to give one particular algorithm to do it, and it's going to be an iterative algorithm, as you've seen many times in the course. Okay, so how do we do this? All right, so this will be a little painful without copy paste, but we'll make do with it. So we have these 3 points, and what we do is we initialize randomly some center mu1 and some center mu2. Okay. Now, when I said that we're going to get out this assignment, I just introduced this new notion, which are these cluster centers. They're going to be points in the space, and the idea is that for every point, I'm going to say it's in cluster 1, if it's closer to mu1, then it's closer to mu2. Okay? And I'm going to try and move these points so that they're at the cluster center. And so the means here refers to the mean of their cluster. So if I were to give you all the points in the cluster, say this point's here, you would expect the mean is right there. That's where mu2 should end up. And the mean of this cluster, mu1, should end up right in their middle. Intuitively clear what we're after? That's the object that we're going to solve for. That's how we're going to get to the clustering. So far, so good? Okay. So now, what I've just described, I'm going to try copy paste again because I'm a glutton for punishment. It should work. It worked earlier. Let's try it. Copy. Oh, so tempting. No, does not work. All right, awesome. Okay, we will then put all these up here, and I will draw it one more illustrative time to do this. I don't know why it doesn't work in this mode now. All right, so how does this work? So I'm going to take those points. Here's my very critically drawn thing. I'm going to have my current guess of the mu I. So here, I probably switched colors. I apologize if I did that. Shouldn't really matter, but I'm not going to be consistent about that, I guess. Here's my points. The first thing I do is I compute, this is the line I said out loud, for every point I figure out which one is closest to. So this point is closer to mu1 than it's closer to mu2, so this is going to be in mu1. Okay? So let me color that character blue. Okay? This point looks to me to be closer to mu1, I'll put mu1 there, than mu2, just barely. This one, I don't know, kind of seems a little closer to mu2. Clear what I'm doing? I'm comparing this distance and this distance. All right? Now, in this way, I go through and I start to compare all of them. Maybe I'll make this character closer to mu1, right? Okay, so this is me implementing this line right here. When I say closer, I'm looking at the distance. You could say, does it matter that it's squared? Not really, but I'll use the square later in a convenience, because it's just a minimum, right? Just saying which points am I closer to. Don't let the square bother you. Euclidean distance. Cool. All right, now, when I do this, I have to do the second point. I have to compute new cluster center. So what's my algorithm going to be? I start with guesses, and hopefully, as we said, mu1 is going to migrate down here, and mu2 is going to go up there. Now, what if, by the way, just as I think, what if mu2 migrated over here and mu1 migrated over there? Would that be bad or good or indifferent? Please. It wouldn't matter. And this is the key point in unsupervised. I don't know which cluster is mu1 or which cluster is mu2. There are no labels. What I care about is that I got centers that were at the right spot, whatever their labels are. Okay? All right. Excellent. Oops. Monkey. All right. Gotta stop drawing in weird ways. All right, we'll get there. Okay, so now the next part of my iteration is this character. I want to compute the new cluster centers. So what I'll do is I'll look at all these points, let's say for the blue characters, and I'll compute their mean. And so their mean, probably lives somewhere about right there. This is going to be mu1 at time 2, I'm going to call it. Clear enough? It's the average of these points, computed however visually crudely. Right? How do I compute it? Well, I just add all of them and divide by the number that are there. Okay? It is really their arithmetic average. Mu2 will get a similar one. Now, if I did my job correctly, that's all a big if. Now notice mu2, I'll put 2 here to denote it. These characters have all gotten closer. Okay? Now when I do this, I then have to loop back. It's an iterative algorithm. Now if I look here, all of these 3 points are now closer to the mu1 character, and all 3 of these are closer to the mu2 character. So all of these would be blue, and all of these would be red. And then where is their mean? Boop, right where I claim they should be, after I run the next step. How do I know at the next time to stop? Exactly right. If I run this algorithm again and I get exactly the same information, the cluster assignments are the same across time step, then it's not going to change the center, right? So this algorithm would just loop forever if I continued to run it, so I'll stop it then. That's the cluster that I got out of this. Is that intuitively clear? Awesome. So now you know k-means. All right. Now, a couple questions. All right. Does it terminate? It's actually not obvious, but guesses, please.
There are only finitely many ways to cluster, and it's deterministic. So we'll eventually have to loop around.
Yeah, great, good intuition. So the intuition is, hey, the underlying clustering is deterministic, and so potentially you could just, you only explore all of them after some point in time. The challenge with that is it could oscillate back and forth, right? So I think you're thinking in the right way, but you were going to say.
I was going to ask, what if you have a situation in which you have a ridiculously scattered amount of data and it's very difficult to assign any kind of cluster or boundary?
Awesome question.
Are you just going to end up in a sequence of constantly changing the view that will never settle down anywhere?
Yeah, wonderful question. So both of you are thinking about this in exactly a very interesting way, and I think you both have kind of the right intuition. So the question is, what if I have points, just to kind of go as you said, what if there doesn't really exist a good clustering? We're going to come back to that in just 1 minute. So I want to come back to that. It's a really important point that you're making. The second one, when I think about, and that's the right example to think about, what would happen in kind of the bad case of what would bounce around with the muse. Now, the thing that would really unsettle the muse is somehow if they weren't kind of making incremental progress in some way. So if they're just flipping values, that's kind of too discrete progress. That could actually oscillate forever. It turns out that underneath the covers, which is kind of amazing, is this functional, this least squares functional, this is actually monotonically decreasing. So it means over time, if you think about why, you should go through the arguments in the notes. Over time, that average, that L2 distance is shrinking. But it doesn't say the rate at which it's shrinking. It could shrink very slowly, and both of these examples are really good ones. If you have something which is really spread out, maybe it's just kind of fighting about one point, right? There's these points which, like, when I move the centers, like there's a big mass and then there's these things around the edge. The worry would be that those, kind of points that are very distant are kind of pulling the cluster centers and they're kind of fighting about this point, but the mass doesn't let them, cleanly solve it on each iteration. So that's the picture. And this says, that really doesn't happen. It actually still goes cleanly. Now, it could go really, really slowly. It doesn't say anything about the rate. Okay. Here's another question. Does it find the global minimum? It is an NP-hard problem. So it'd be super suspicious. So one of two things would have to be true. Either it would decrease so slowly, because it's an NP-hard problem, that it would take an exponential number of steps. Or it could find not the right answer. Both of those are possible from the first thing. It picks not the right answer. Okay? We'll come back to that in a second. There's another question.
What is an NP-hard problem?
Oh, sorry. So NP-hard problem is a notion from complexity. You don't need to know it for this class. It means that it's expected that a problem is easy to verify in polynomial time, but takes potentially much longer to get the right answer. So it's a notion of being a computationally hard problem. It just means something that's unlikely to have a simple, efficient solution. Yeah. Great question. Sorry about that. Yeah. So the NP-hard problem gives you some clue that this thing won't have a minimum. And indeed, it does not. Please, you had another question.
Local minimum?
Awesome question, yeah. Are there multiple local minimum? So because it converges, and because you have that it's not finding a global minimum, you suspect that in fact there are these local minima that it can get locked into, and indeed there can be multiple of them. And sort of what can happen here is this kind of thing that we're talking about, that indeed, yes, there are multiple local minima, and it's not well defined. Go ahead, yeah.
Jump around to start from different starting points.
Exactly right.
At the end of a lower local minimum.
Exactly right. So the intuition is, because you have these local minima, the initialization matters quite a bit, right? Because if you looked, if you think, okay, it's potentially going to end in a different solution, but every step we had in the algorithm that I go back was deterministic. So how is it ending up somewhere else? Well, there's one thing that we didn't talk about, which is this part here. Randomly initialize the centers. That point of where you start, the mu1s and the mu2s, can have a difference on what kind of solution you get at the end. Perfect. You guys got this intuition exactly right. All right. Now, it turns out that a while back, there were some great folks from Stanford folks. They were graduate students at Stanford, and they came up with this algorithm that they called k-means plus plus. And it's one of my favorite kind of algorithms. And they basically showed that they could get a great approximation ratio by weighting where you started those points. So they could show that there was an initialization, that no matter what your data is, they would do a pretty good job. Because with NP-hard, they couldn't prove that you would get an optimal solution, but they proved that starting with that right solution, that would be actually the way to do it. And interestingly enough, if you use this package, which is like a very common Python package for traditional machine learning called sklearn, it's actually implemented there, and it is actually the default now. Okay, and Vasily did it when they were grad students, and there's a little Wikipedia page about it, which doesn't render too well. Please.
Is it an approximation ratio?
Yeah, so an approximation ratio means basically I'm gonna tell you that my solution has some fraction, some ratio to the true solution. So the optimal has some cost, if you like. And an approximation ratio means I can bound what that cost is. It just means that. Now you could say, why do I care about the cost? That's a separate issue, right? Like the cost may not be a meaningful structure. What it really says qualitatively is initialization matters, and there's a smart way to do it. And some wonderful, smart Stanford people like you who took some precursor to 229 or 229 itself figured out how to solve it. That's what I cared to get across. Awesome questions, please.
At the bottom of the previous slide, when you say like repeat, does that mean, can you explain exactly what's going on with repeating?
Oh yeah. So this repeat until the cluster stay the same. Yeah. This is what we talked about verbally. So there's no additional content. But as we talked about, these two steps, assign to a cluster and compute a new cluster, we're going to iterate again and again. And what we thought about is there's nothing in here that says to stop iterating. But there's a natural condition to stop iterating. There's one natural condition, actually, which you use in practice. Run some number of steps and call it a day. You're all familiar with this condition. A second one that is traditionally run is, well, the clusters are eventually going to get fixed. You're getting stuck at a minima. And then you just stop when the assignments are there.
So we're not repeating initialize, we're using
exactly right. Yeah, this part is the part from as you said, that you're initializing. We're not reinitializing on every step. Wonderful questions. Please.
Some lectures ago, we got the situation that in very high dimensions, it's kind of hard to think about like non-complexities. So does it apply here? Like if you have many dimensions, it will be probably easier to have
This is a phenomenal question. Let me see if I have it on the next piece. No. Okay. So the question, there's two questions that I want to get to here. So the kind of repeating as you went back to is one of the things we discussed earlier is that your intuition about what happens with points in high dimensions is a little bit weird, right? It doesn't look like 3 dimensions. And so weird things can happen in high dimensions with random points. Your nearest neighbor and your farthest neighbor are about the same distance. Stuff like that. Like if you sample from the sphere, you get like the shell, if you sample inside the sphere kind of thing. Okay. So this relates back to your point about, this random scattered data that's out there. If your data has no structure in it and it's random, then running k-means on it is kind of a bizarre thing to do. And the reason it's bizarre is what k-means has to have underneath it is some meaningful structure. And this is exactly, you're both thinking exact the same way. If your data has latent clusters, you believe it has latent clusters. I was at a talk earlier today where someone was talking about clusters in gene type, different gene types for different, expression. The clusters we believe are meaningful. We believe there are homologs. We believe there are genes that look kind of the same and they should actually cluster. K-means is designed to say if the data look like that, we should be able to pull it out. And even if it looks like that, we may not be able to pull it out because of all the caveats that I put here. But that's the intuition, if it makes sense. So there has to be some structure. And in general, this structure is quite rare, as you were thinking about before. If you have a spray of points that have no structure to them, k-means will return something, but it won't be meaningful. And so this type of algorithm, these unsupervised, which you guys are phenomenal, you got right away, they really only make sense if you take that data in this incarnation and actually examine it or check it in some other way. And so a lot of the places where you'll use unsupervised algorithms are to get a descriptive feel of your data, or if you know there actually are clusters inside it and that this is something that's meaningful to pull out, like in the biology example. We'll see another one later. Maybe it's the next lecture, where people are looking for data from particular stars. And the stars have very different emission patterns. And so they know that data is meaningful and they have a different way of checking it. Okay. But that's kind of the mental model of how you use it. And you have to see there's a lot of just raw modeling. Another one which people always ask rightly is, how do you pick K? So we talked about K being equal to 2. But this conversation, as we talked about, you could make K 5, 10, 20. How do you pick it? Well, it turns out that when you pick K, you are making another modeling assumption. You have to have some intuition about how many K are actually in your data set, how many clusters are in your data set. If we go back and look, I'll draw this picture. So let's say that I have, these points. How many different clusters are here? Well, you could say maybe there's 2. You say, no, I think there's 4. Both of those are kind of correct 3 gets a little wonky, right? 3, if you try and think about what it looks like, you're like, which 3 do I pick, right? Maybe I pick 2 and 1. I don't know. Maybe I pick these 2. The point is that this is actually very underspecified. And so at first, the reason I like this so much is it's a simple enough algorithm to think through effectively all of these issues. That's like one of the real challenges when you start to do more unsupervised modeling, is that it forces you to think about modeling challenges, because otherwise the answer doesn't make sense. Which sometimes if you're doing kind of a linear model, you don't think as much about what the modeling assumptions you're making are, but they're still there. Machine learning only works under assumptions. Okay? That's the trade. That's the idea. Fantastic, please.
With different Ks. Like average cost.
Yeah. So the question is, can you run k-means with different random initializations and see what you get? How would you tell the difference between? Yeah, so you run with different k. So I have my solution with k equals 1, k equals 2. And by the way, if I run k equals 2 this some number of times, I may also get different answers, right? Because we talked about the initialization matters, where I randomly initialize. So now how do I decide which one of those are good? The answers are good or bad?
Based on your average cost function.
You could take the average cost function. What challenge with the average cost function can you imagine comparing across values of k?
It's like as we have more points, you build.
Awesome. Yeah, exactly right. As you increase k, you're getting back to this. You're getting finer and finer clusters. But is it really better? I don't know. Please.
So is it safe to say that the choice of K is fundamentally motivated by a modeling question, but the number of resulting clusters that you get out of that with respect to whatever you're trying to model is also a modeling question based on what answer you are trying to get at?
Exactly right.
The question, I'm not sure it's clear, but I'm trying to say that in this example, perhaps if I were to say, there are 2, if I ran that there are 2 clusters here, there might be an interpretation that I can assign to that, but it's fundamentally based off of other principles in the model that are I understand.
Exactly right. And we'll see an example that comes up like this later. But you're exactly right that when you say what's going on in K, there are 2 clusters. You're implicitly saying something about the state of the world. You're translating that into K. There are places where the event happens and where they don't happen, and I want to bring them together. Or you're saying something like, I know there are 5 sources of data, and I want to cluster those 5 sources. I happen to know that overall. Or you're saying, I don't know, back to the question about exploring K, and I want to see under different K what might actually fit. All of those are reasonable uses for this algorithm. And as I said, that's why it becomes a little bit more conceptually challenging to use. It's not as straightforward as run the linear regressor and fit the line. Okay. Awesome questions. These are really great. Others? All right. Oh, please.
Can you not do something where the more K you add, the higher K gets, the smaller distances of each point.
Right.
But can you not plot something with that cost against and then look for an inflection or something?
Wonderful idea. So the idea you're telling me there's nothing you can do and it has to all be like, slaughter a goat and look at the blood. And I'm telling you that's the truth. But you're asking, are there other measures? For k-means, there aren't really great other measures because you need some other structure. We're going to see something Gaussian mixture in a second that loads up a probabilistic structure onto it that allows you to talk about likelihoods and other kinds of things. You can certainly start to, basically what your intuition, which is dead on, is, aren't there other secondary characteristics of goodness of fit? And I would say goodness of fit that just depends on the same model parameters you have may not be as helpful as auxiliary sources of information that could tell you that's a really good fit, right? You're like, I know that the clusters should all be I have some spatial knowledge. They should all form crescents when I'm done with them. That may be an idea that helps you validate the clusters just as well. And so I tend to fall in that camp. We'll see next lecture a different thing called PCA. And in PCA, there actually is a test that has a goodness of fit that's almost exactly what you're describing, which says, it has to do with the eigenvalue tail. It will make sense when we come to it, but then says, this is how much variance I'm explaining underneath the data from the goodness of fit. Here, we just don't really have the structure. That said, there are tests in the literature that are along the lines of what you're saying. I'm just telling you intuitively, I haven't found them to be particularly useful in my own work. Yeah. Awesome questions. Others? All right. Okay. Yeah. So this is just making the point that you all made for me. I made these points earlier, and they're in the notes, and you already made the point about random restarts and everything else. That's all that slide I skipped was. Okay. Now to our second character today, and this will have a little bit more math. This is basically going to be k-means with a little bit of annoying math and Bayes rule. Okay? I want you to think intuitively it's k-means, but we're going to estimate everything we do with math and Bayes rule, but it's really doing fundamentally kind of the same behavior. And instead of having clusters, we're going to have mixtures of these Gaussians. All right. So here's the picture that I want to draw. Okay. So this is a toy example. I looked this up a couple years ago because with some friends. This is like I looked into the literature and I tried to find what are good examples of using mixture of Gaussians that I thought were fun and interesting. And this was from some friends at the University of Washington. And they were looking at for quasars and stars. Okay. They're both sources of light. And the idea here is that these quasars and stars are shooting off light. Those photons are coming, they're hitting us, and we're counting the number of photons. Okay? And so at a particular time point, we're going to observe a bunch of photons. I'm trying to draw this picture so it makes a little bit of sense. And then maybe there's something. Okay, every cross X here is supposed to be a photon, okay? That we observe. All right, so this is what we're given. And then what we like to do is we like to understand the sources of data. And these sources may have different shapes. I don't know anything about the underlying physics, so let's just say these are quasars for the moment. That sounds good. These tight bundles are, the idea is that they're going to shoot a ton of photons, they'll have high density, but they don't have a ton of spread. There are other objects in the sky that are going to have large spreads, potentially. They're going to have some distortion, they're going to shoot like a disk, okay? And they may have corresponding less intensity. Okay? These are the types of objects that we're considering for the moment. Go ahead.
Wait, what are the axes here?
Oh, this is spatial. This is X and Y in space. Like imagine it's a photon plate that I've taken a picture of some region of the sky, and this is the plate where the photons are hitting me. Yeah. Thanks. Sorry for that. Okay. So the point that I wanted to make here is what we're going to do is we're going to assign each photon to a light source, but we're going to have a probability of assigning to source J. So we're going to compare this with the k-means. Instead of saying it's exactly in this cluster, making a hard threshold. Remember we were worried about these points that were on the border? We're going to allow ourselves to say 60% in cluster 1, 60% in cluster 2. Here the terminology instead of cluster I'm going to use is from a source. This idea here is you say like, oh, these are very likely to be from one source. This is very likely one source. This is very likely one source. These characters here, I'm not sure which source they're from. That I can express through this probability vector. Okay? So the sources are fixed, but the probabilities are what I have aligned. I don't have to do a hard assignment to a cluster. Clear now? Okay. Okay. All right. So that's what this PZI equals J. If you do look on the online notes, there's like a pretty nice diagram that I drew. So the takeaway of this is, as I said, hard assignment is what we were doing before, but now we're going to do these probabilistic assignment. And so the probabilistic assignment, as I showed you, is hopefully you remember how the Gaussians look. They have this kind of shapes, either kind of circles or long ellipses. They're ellipses that we can put and rotate, right? That's how Gaussians look. And that's going to allow us to say, from that center, the same as that mean, it's going to allow us to assign how likely every point is. All right. All good. Okay. Okay. All right. All right. So here are the challenges. Okay. So what are the challenges? There are many sources that are possible. Okay. We're going to assume we know the number of sources K, just as we assumed before. You know that you're going to assume for this run of the algorithm, you know the number of sources. The sources can have different intensity and shapes. You may have some that are shaped like this, some that are shaped like this, all the Gaussian shapes. They're all going to be Gaussian. The shapes are going to be modeled by, remember, their mean, and then their covariance, their sigma. Here is sigma squared, because I'm going to do things in 1D for the next couple of slides. We also do not assume we know the number of points for each source. Okay? So it could be that there's one source that puts out a huge number of points, and another source that puts out a very small number of points. And we're going to try and learn that also from the data. Having that information would be nice, right? If you knew that the pulsars were putting out some number of points, or quasars, that would be really useful. In this application, you don't. Okay? All right, so far so good. Any questions about the assumptions, what they mean? We know what the shapes are, so think about mentally we're putting down shapes. We can rotate them, we can make them, different sizes. They have different means and different variances, but we don't assume we know the number of points in every source. Okay, cool. All right. Oh, this one made it through. I was very happy to make it through, I guess. And so here you see the shapes of Gaussians to remember. You have sphericals, you have diagonals, and you have, kind of the full meal deal. Okay. All right. Please.
We don't know the number of points inside each cluster, but so each source, but we know the number of sources. What happens in the case where no points get assigned?
Oh, wonderful question. Yeah. So let's come back to that in a minute. So the question is, what happens if I pick a number of sources and that number of sources is incorrect? And one way it could be incorrect is that I think there are too many sources, or there's a source rather that I don't measure, that I think is in my data set, but I don't measure or I don't assign something to it. When we run through the arithmetic, you're going to see exactly what happens. There's going to be some support that's there that will cause this to be, an interesting phenomenon. And you'll see kind of how it degrades at that point. But this is exactly the right way to think about this. Yeah. Other questions? All right. Okay. So let's do a 1D version of the problem so that I can talk to you through one of the technical issues. So here's the model that we have. So this is, remember, there's always a forward model. And we have, in this little setup, I'm going to give myself two means. So imagine there's one mean here, and there's another mean here. Okay, this is mu2. And this is mu1. Okay. Now, what happens when we sample from these is that we get a bunch of points. Okay? Some points here, here, here. And the way that these happen, right, is if you think about it, there's some proportion of how often we're going to sample from each one. So we flip a coin, say that's 60% in 1 and 40% in 2. We flip that coin. We then go to the right mean, and then we sample according to that Gaussian, right? And so I'm drawing them like they're in order, but they're really not in order, right? They're just like points that are sampled from each one of these. Okay? Now, when we look at these points, you would probably be tempted to say these points here are probably from this source, and these points here are from this source. But we could also have points that are, right on the boundary here. Oops. Where they're kind of, it's unclear where to come from. Now, if we knew the sampling process, we could say this point maybe came from 1 or 2. But all we observe is the bottom line and the points that are on it. We just observe the line, okay, which I would normally love to copy paste and have a big reveal. We just see this. Okay, this is all we're given. We don't get to see any of this stuff which defines the model. Okay, we're going to try and learn that. Okay, now, if we knew the labels, this is a really interesting, easy problem. If I told you, oh, this one is blue and blue and blue and blue, and oh, this questionable one, that's also blue. Red, 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 red. Well, this gets you back to your favorite GDA, right? And so it will turn out, effectively, what we're going to try and do is we're going to try and, as you imagine, guess the labels and then run something which looks just like GDA. Okay? So if you remember GDA, what you would do is you would try to fit to those points. You had two class labels, red and blue. You would try and get the best fit for Gaussians for each of them. Okay? That was what we did 2 weeks back. We'll derive it again. Don't worry if you don't remember it. But the key challenge is we don't have those labels. So just intuitively, how do you think you solve that challenge of not having the labels? Yeah, so one idea is to randomly assign them. So we're going to try and maybe first we randomly assign them. Then how do you imagine the iteration would go? Okay, that's not that well. Yeah, it's a great answer. Yeah, not that well. I like that answer. Oh, yeah, please.
You assign it to like the class of them.
Yeah, so one example is you have some guess of where these clusters are. You first label them as if they're kind of closer in that cluster with some probability. You have some guess of the sampling. And then you see now, instead of how close they are in space, you see how likely they are. You update each point, right, to say, is it likely, how likely is it to be in each cluster? and then you resolve the means back and forth. That's what to keep in your head. I'm going to put some math on, but that's the intuition. Does that intuition make sense? We'll see the math if it's not crystal clear what to do, but at least the template should look a lot like k-means. Please.
What's the same shared variance that we have in GDA here?
Oh, wonderful point. So you don't need to have the same shared variance that you had in GDA here. The shapes are going to be different across all of them. And we talked about, that as well last time. So you can solve that. The GDA was meant more as an analog. We're going to solve this without having to know GDA. I just want to highlight for you the piece that's new. And the piece that's new is no cluster labels. You've actually seen every piece of this algorithm effectively in some previous lecture. This is the twist, just this piece. Okay. We'll derive it all from scratch. You don't have to make that association, but just so you're trying to isolate what's new and what's not. All right, let's be a little bit more formal. So here's how we're going to do it in this 1D version. We're given x1 to xn that are in R and a positive integer k. This is what we're given as input to the problem. Our job is to find this function p, that for each data point I, 1 to n, and each source j from 1 to k, we find a soft assignment of the following form. So rather than doing the hard assignment, we say the probability that xi comes from source j is exactly this. This is just a table of numbers. For every point, imagine there's a k vector that says exactly where they come from. Okay? That's the way to think about it. Now, this probability, if it were just wild, it's not really clear how to assign anything. So we need a model, a forward model. And I showed you that forward model on the last slide. Now I'm going to write it mathematically. Intuitively, it should pick which cluster it's from with some probability, and then it should sample from that cluster probability. So let's write that down and see exactly how that works. There it is. It says the probability of x and zi is going to factor by Bayes' rule. That's not a controversial statement. The zi's are basically going to be selected as a mixture of sources. Okay? So what's going to say is it's multinomial. This is where we don't know the probability, but imagine you had a fixed probability. So you say it's 60% here, 40% there. You're going to pick 60% cluster 1, 40% cluster 2. You flip a coin with that bias. That gives you a cluster that you're looking at. And then, as was highlighted earlier, which was wonderful, given that you know which cluster you're in cluster J, you have a different mean and a different variance that you look up in your table, and you produce xi. And so I'm sorry if the colors are hard for you, but these things that are in blue, that are highlighted here, that are just a little bit different, those are the parameters that we're trying to estimate. Okay? Okay. So we call zi the hidden or latent variable. These latent variable models are quite common. They're more sophisticated. We'll see more of them. It's where we assume there's some structure. It's latent or hidden because we don't observe it. We don't get to directly measure this. But we hypothesize that it's there, even though it's not directly observed, and it defines this. So if we knew which cluster it is, then it would tell us the mean and the variance. Okay? But of course, this is also a random sample, right? Which is like, somewhere in the space. Is it clear how the forward model works? Please. Yeah, great question. So how should I think about how phi, this multinomial, actually changes? If you knew phi, that would correspond to knowing 90, let's say you have a phi that says 90 and 10, 90% in cluster 1, 10% in cluster 2. Then once you did that, you wouldn't need to do this kind of sample, if you like, at all. You'd be trying to learn this 90-10 weighted by this. We'll see where that comes out in the math. Here, we're actually going to be able to learn phi as well. So it's not really a prior. A prior would be if I told you the 90-10, but we're actually going to learn it. So it's not a prior. It's actually something we're going to estimate from the data. Other questions? It's a totally reasonable thing to put in. The bits. Fantastic. Okay. So we went through this. I'll just draw it out one more time just because I think it's illustrative and to stall a little bit for questions. So we had our mu. Oops, that's a terrible looking Gaussian, but you'll excuse it because you're very kind people. UT. So how does it work? Again, back to it. I select zi with some probability. I guess I picked 0.7 and 0.3 here. I call that zi. For this point that I'm generating, let's say that I picked this particular cluster. Then I sample from this norm, this unit normal, or this normal distribution, and I get this point. That's the forward generating process. And then I do that for every single point. That's how I generate all xn points. Pick this way or this way, then sample. Clear enough how it works? Okay, cool. All right. Okay. All right. So just to recap this, to make sure it's super clear, given a set of parameters, we're going to assess how likely x1 and xn are according to the GMM model. From that description I told you, one of the things is I can now write the probability of those points under various different parameters. So you give me two sets of parameters, I can score how likely the data are and conceptually also get the likelihood function, right? That's what we were after before. Once we have a likelihood function, we kind of get back into the same framework. So the likelihood model of the GMM is enough for us to estimate those parameters directly from the observed data. That's what we're going to try and figure out how to do. The twist here is that ZI is our first example of a latent model. We do not observe the value of ZI, but we know something about it. This is equivalent, really morally, to there exist K clusters, right? That ZI, although we don't observe it, says there exist these K sources, and then we're going to sample from each of them. Clear enough how it works? All right. Let's see an algorithm. It's going to look like K-means, but it's going to have a lot more math. And then in later lectures, maybe like Wednesday, I'm going to show you how it's actually an MLE algorithm in disguise. So it is actually an instance of your old framework. Go ahead. Sure.
From what I understood, it's like about n trials or something. We're counting the category.
Sure.
But how does that apply to
Wonderful question. All right, so let's go back. So the question is, how does this change? I think you're asking, how does this change the estimation procedure? Let me get back, see if I have a drawing. Sorry, I have to scroll so far back. All right, actually, I'll just use this picture. All right, all right. Give me one more second to look. If I can't find it, I will just draw it again. Okay, here it is. This character. Okay, let's go back and see how the phi might intuitively expand our reasoning. And then when we do the math, I want you to check that this actually works. Like, I'm not lying to you. So let's imagine you have mu1 and mu2, and you have this one. And let's imagine I picked it exactly where the points cross. Then it seems like a coin flip. Should this point go to cluster 2 or should it go to cluster 1? Right? Now, if you knew cluster 2 generated 100 times more data than cluster 1, would you be more likely to say this came from cluster 2 or cluster 1? Cluster 2, right? Because you would say, oh, actually cluster 2 is spitting off points. It's relatively rare, all things being equal. That inference you just did is Bayes' rule. And we're going to come to that exactly when we do this, that the phi is allowing us to do exactly that, to tell us that the observed counts are there. Please.
vector then? Because it has each of the...
In this example, it only has to be a scalar because there are two, and it's determined. You know, the last component is determined. You only, if you have, you know, n outcome or m outcomes, you only have to have m minus 1 because they sum. But in general, yes, it would be a vector, a multinomial vector. Yeah, great points. Please.
Can you go to slide 27?
Probably not. Yes, yeah, I'll do my best. Sure. I think this is 27. This is 27?
Yeah.
Good.
I was just wondering, so if you get like the joint probability of like xi and zi, and you just take like one specific xi, and you sum over all the possible classes, would that actually equal 1?
If it's a probability, yes. So let's come to that in just 1 minute to see actually how these are operating on them, okay? All this is saying is the probability distribution for xi, how likely xi is factors as, which this is a tautology. It says if you tell me what the cluster is, and you have a distribution over clusters, you weight that, conditioned on that, says if you're in this cluster, this is the likelihood I assign to you. That integration over all the possibilities of xi is 1 because it's conditional probability, and that's the weighting.
I understand that, but like if the probability of zi, like let's say 0.7,
Sure.
and then you're further like diluting that with the normal, right? So the probability of like a specific combination of xi and zi would be even lower. So then that just
Yeah. So you okay? So what is confusing to you about this is these are total probabilities that are here, that are there. So you're going to have to sum over all of the zi's that come into this and integrate over all the xi's that come into this. That would be the same that you would do here. It's a joint probability. Yeah. So that sums to 1. They don't individually sum to 1 in the way that, like, if you just fixed one value and did the rest. Yeah. Great point. Great point. Okay. Yeah, so there's some math coming. Okay. I believe we're here. You tell me if I'm wrong. All right, yeah, we're here. Okay, cool. These are phenomenal questions. Please keep asking, right? We are in no rush to cover this. So by all means, it's more important. All right, so here's how EM works. We talked about it at a high level. We're now going to go one little click down. So the E step, which I am highlighting for later, that terminology will make more sense later, but I want to build, to it. We're going to guess the latent value for Zi. So for each point I 1 to n, we're going to get a probability over which source it's likely to have come from. Okay? The M step, given that estimation, we're then going to update all of the parameters, all of the mu's and the sigmas and the phi's, and that's going to tell us, that's the step where we're consolidating the cluster means. This is where we're doing estimation instead of cluster means. And then we're going to try and use that to estimate, given where we think the clusters are, how likely each point is. Back and forth, all right? So let's do each step in detail. Schema of the algorithm should look a lot like k-means, right? It's kind of the same thing that's going on, just with this more probabilistic take. So let's walk through what they are, and hopefully this will become clear. So what you're given in the E step, you're given x1 to xn, and then you're given some current estimate of your parameters. So the parameters are telling you how likely every bump is, every source is, the means and the variances, picture the circles. And then the idea is for each data point and each cluster, you're going to try and estimate how likely the probability that's there. And so you're going to write Wij in terms of all of the parameters that are there. So far, so good? Okay. So how does that happen? So this is what we're after. How does this happen? So we're going to decompose it with Bayes' rule. This basically says this conditional probability, we're going to look at the joint total probability of xi and zi, conditioned on all these parameters. So far, we haven't done anything. This is pure syntax. We're then going to split conditionally on z. So we're basically trying to, what's going on here intuitively is, we have a model that goes in the other direction, if you like, where we have one that's z conditioned on x, and we're going to try and go to x conditioned on z. That's all that's happening in these slides. This is kind of a standard argument. It seems weird the first time you're seeing it. I appreciate that. But this is all we're going to do. We have a model that's forward. We want to invert it conceptually so that we can go estimate the parameters. All right? And then we apply Bayes' rule one more time. We sum over all the possible clusters. Okay? So we're looking at one particular clustering, which is for some point I in cluster J. And we say, how likely is this cluster? Or what is this Wij? Well, we just normalize by looking at all the probabilities across all of them. And expand over all, this is summing over all the possible clusters. That's what L is doing here. Okay. All right. Now the key point is, all of these terms are computable directly from the parameters we saw on the last slide. Now that we've done the decomposition, it's in the model framework. These conditional probabilities in this form are all just going to be these normals. So you know exactly how to write that out. I could write out x of this and all the rest. You know how to do that. Okay? The probability here, you know this. You just substitute in the natural parameter, and that will give you these numbers here. Okay? So the point that you should be hopefully convinced by is this Wij is nothing more than rewriting it directly in the model with a couple applications of Bayes' rule. It really is the estimation. And this, may seem mysterious because there's all this terrible notation everywhere. But when we were informally reasoning earlier about how likely a point is, I'm like, this is Bayes' rule. This is what we're doing. We just inverted it. Cool. All right. At that point, we now have an estimate in the M step for how likely every point is to belong to a cluster, given our current guess of everything, the phi's, the means, everything, all the shapes. Now what we're going to do is, same thing we did in k-means. What did we do in k-means? We then try to compute the new mean based on what we thought was in the cluster. Now we have a likelihood, so it's a softer version, but we have to then go ahead and compute where's the mean of that thing, what is the fraction of elements that are present, that's the phi, so on. So what is the fraction of elements from source J? Well, it's the expected value. Okay. Now, this may seem ad hoc to you or may seem natural to you. We will derive why it's that estimate, but intuitively you're estimating this mean or the fraction. What it's saying is, this says how many points are in J. If it were 0 or 1, this would be actually the fraction of points that are in there, right? If you knew precisely every single point in which cluster it was, this would be the exact fraction of points. But because we only know it probabilistically, so we know that it's in cluster 1 and cluster 2, but it's definitely not in cluster 3. So we know 1 and 2, 50%, it counts a half to one cluster and a half to another. That's the difference from k-mean. That's all it's saying. Then when we compute the means, because we also don't know perfectly which points are there, we compute them in a weighted way by exactly those weights and probabilities. So before, if we had, for example, those 2 points that were uncertain, it computes kind of half to one cluster and half in the other. And then we normalize so that we get, this is the sum over all the weights that are there. So we get a proper mean, a weighted mean. If all these were zeros and ones, this would look exactly like k-means, right? This would be your mean assignments that we had from before. We didn't have to estimate the fraction in k-means, but now we do. If these were 0, 1, convince yourself that this would exactly be the same mean that we were computing in k-mean, the centroid that we were doing. Okay. Awesome. Okay. So, on that, how does this work? Okay, so any questions, please? Yeah. Oh yeah, sigma is updated here too. We will come back to the actual form to estimate sigma, but it's exactly the empirical way that you would imagine to do it. I just didn't derive it here. I may derive it a little bit later. Okay. But yeah, so the question was, will you hid all these sigmas for me. We also have to estimate the sigmas. And intuitively, they will follow exactly this framework of you're going to look at the outer products of the xi's, weighted, and you're going to take their average. We'll talk exactly about how to do that estimation. Very, very good catch. All of these parameters need to be estimated. Then what do we do? After we do the E step, we do the M step, then what happens? We do the E step again. We do the M step again. We iterate, we iterate, we iterate. Okay? It looks a lot like k-means if you think about it. So far, so good? Okay. There is an example in the notes of running these particular points and how they look in E steps and M steps that are in the notes, but they didn't render here because of my mistake. And so there's a whole diagram that's in here that I would advise you to look at. I would say the content, intellectual content of it is not very high. It looks just like the other things. You start with the centers. You move the centers and which points are there. Then what happens that's different in k-means is I'll just draw this piece because it's probably better than gesturing in my hands. So let's say that you had a bunch of points over here and I'm drawing them in red because I'm saying you thought that these were the points that, are really likely to be red and blue and so on. And this guy, is kind of purple, right? When you go to compute the means for this, you're going to compute the means, and as was just pointed out, you're going to compute the sigmas. You're going to compute the shape of these points and their center from the given set of points that you tell me are red, and with what probability, okay, in that weighted way. And so if you picture it as it's going, it's figuring out the shapes and the locations of all the sources on every iteration, then uses those shapes and iterations to rescore all the points. On the next iteration, it's probably going to say, oh, that's pretty likely that this is actually from there. If, however, this red thing had been super long, okay, all these points are in red, and this is what it thought. And I thought it was a very narrow thing so that this distance became meaningful, right? So that it's an exponential with a very tight variance in one direction. Then at some point that variance gets so tight that this thing gets kicked over there. Clear enough how it works? Please ask a question. That was kind of an ad hoc, on-the-fly explanation. I'm sure it left a lot to be desired. All right. Feel free to ask me. Okay? All right. Okay. So, at this stage, what am I going to do next? So what I'm going to do next is I'm going to tell you about this little detour through something called Jensen's inequality and remind you about convexity. And the reason I'm going to remind you about convexity is we're going to use it in one key step of the proof that otherwise seems to cause a lot of confusion. It is literally the definition of convexity that we're going to use, and that's going to allow us to do the entire estimation procedure for what we're doing. So what's happening as we do that back and forth that we're doing, the question is kind of that should be looking in your head is, what does that likelihood or functional look like that we're kind of operating on? What are we actually minimizing underneath? Remember before there was this kind of least squares lost. Now the loss is more complicated. It's this likelihood and probability thing. What we're going to do is we're going to use a convex estimate where we're going to allow ourselves to do this one inequality called Jensen's inequality that's going to move basically an expectation inside that's going to allow us to go from something that's hard to compute, something that's an easier surrogate to compute. That's going to be the whole game. Before we get there, I'm going to show you Jensen's inequality so that it's really clear in your mind what the trade-off is. Hopefully it's a nice geometric picture. Okay, it's going to take me a little bit to set up, so we'll go through that over the next little bit. Okay. All right. Okay. So what is convexity? If you've already seen this, don't worry about it. All good. If you haven't seen this, hopefully my presentation does enough to do it. So imagine that's a real circle, not one weird thing that I've drawn. Okay. Here are two shapes. This one is going to be convex. This one is non-convex. What does this mean? Well, it means, this math says, if you pick an A and a B, the line between them is always contained inside. No matter how I pick A and B. Okay? This term here is just the line. This is the set omega. So far, so good? This one is non-convex. But now notice that A and B here, that's inside, that's not good enough. It has to be for all of them. This is non-convex because of this line. Here's A and B. So far, so good? All right. Okay. Now, that's convex as sets. What we care about are convex functions. And what we care about here is the graph that they're on. Now, those two things that I just drew, which seem kind of ad hoc, actually are nice canonical things. So the canonical convex function is a nice bowl-shaped function like x squared. Okay? So here, I have some point Z, I have some point A, I have some point B. This is my f, this character is f of Z, okay? Here, or f of x, I should say, since I picked Z as a point. Oops. We hope that this function is convex. And in fact, if I color this properly, this thing here, this set as a graph, the function is convex if that set as a graph is convex. Okay? Now, what does that mean? Right? In symbols, if I take a point here and a point here, what does it say about the chord between them? Well, it's got to go through the set, right? And so that means that this chord is above the rest of what happens. So far, so good? So in symbols, it's just saying this, which reduces to that. Okay? So geometrically, hopefully it's clear. There's a point here. If I take 2 points on the curve and connect the line between them, the function graph is going to go underneath it because those things are going to go in the graph, which is the part of the set that's above the function value. That's what the graph means here. Y is bigger than f of x. Okay? This is what the graph, I'm trying to draw the graph of x squared. Whether I succeeded or not, I mean, certainly I didn't succeed exactly, but, if I'm close enough. Here's another function, some quartic or something, that's not convex. And the reason is exactly as we talked about. Its graph goes below. Clear enough? This is non-convex. Okay. All good. Now, any questions about this? Everybody's happy? Please. Yeah, any Z between A and B would certify that it's not present. Wonderful question. Okay, cool. Now, here's a nice characterization of convex, and one that we'll actually use. If f is twice differentiable, and for all x, for all x, f prime of x is greater than or equal to 0, then f is convex. Okay? Now, why is that? Well, use Taylor theorem with remainder. Write out the definition, and notice that you get out this nice C here that's greater than or equal to 0 because it's a square. That's all that's going on. Okay? So these bowl-shaped functions, these are the convex functions. Okay? That's all we're saying here. And that's going to allow us, when we use before, we're going to use the fact that this chord, we're actually going to use on concave functions, but this is going to provide us with some nice geometry about what kind of estimate we have. Okay, awesome. All right. Now, in fact, we'll also worry about these things which are, strongly convex if it's strictly greater than 0. And that's just terminology. Okay? Please.
Explaining what C was and
Oh, yeah, great question. Okay, so basically all I did here is I took this function z and I looked at, I subtracted out both sides just as I was looking at the two pieces. That's going to subtract off the first terms. Then I'm going to get this nice kind of convex relaxation from this term here, right? By putting this piece down here. I'm just taking the terms that are associated with f prime. And then what I'm claiming here is, I want to claim that this line, these guys are above z, and my point is when I do that, any mixture of those values, those convex mixture of those values, it's going to be equal to this character here. F of z is this character here, plus some c, which is positive, or non-negative, and so I have that this function is convex. Please.
What is it for approximation using the 1/2?
Oh, because so the error term here, so the error term, you're right that there should be a 1/2 here. So that is definitely an error, that this should be over 2 because it should be the whole thing. The part here is that in the error terms, I'm just picking some eta A's and eta B's, and that's the way the error term works. But you're 100% right that there should be a 1/2 here, normalizing it. Wonderful point. Good catch. Awesome. Okay? And the point is that you're then getting this mixture, no matter where I get the mixture of F and A, anywhere on that line, that's the line between them, I'm basically always getting this sum of a C, which is non-negative. Okay. All right. Cool. Okay. So far, so good. This is what we actually care about. For Jensen, we care about that the expected value of f of x is greater than or equal to f of the expected value. This is what I mean when we're able to push something inside, if you like. So let's look at a simple example here, where x takes the value a with probability lambda and b with probability 1 minus lambda. Then the expected value of x is exactly this mixture, which we just talked about on the previous slide. But f of this mixture is exactly z. These are, Jensen's inequality is the definition of convexity. Sometimes it's presented as some mysterious consequence. It is the definition of convexity. It's like the whole reason we're after it. Now, this piece here, you could say, well, you only proved it for 2 points or something. Okay, 2 you can do induction. Induction can get you to the continuous case. This is it. No more. Okay? All right. All good. Okay, so far good? So all that you care about is this notion here, this direction goes exactly the same as you would expect for convexity. That's all we're going to use. That we can move this inside and we're going to get some slop. All right. All right. We say that a function is concave if negative that is convex. Does anyone remember what the canonical concave function is? Negative x squared would be a good one. But also logs. We're going to use logs a lot. This is going to be really important for us because we apply this function to logs of probabilities, right? That's what we're going to do again and again. So we're going to use these concave functions all over the place, okay? And in that case, Jensen's inequality has the sign reversed. This is what we're actually going to use. Now, if it were linear, it's concave and convex because the derivative is exactly 0. That's pretty nice. So linear functions are great, right? And in that case, this is an equality, right? That's linearity of expectation. You should expect that. Just a sanity check. Okay. So hopefully that extremely fast detour through convex analysis in Jensen's at least warmed you up when we go through here. And what the flag is, if it doesn't make intuitive sense to you, that's totally okay. But at least you know where to look. Okay? So let's look at the algorithm as maximum likelihood. So here's what we're going to do. We have a likelihood function which says, given all of our parameters, there's some likelihood on the data. Standard thing we've been doing forever. How come I can write this as a sum? What am I assuming here? Some ID-ness. It's always ID. Just say ID. Even if you don't know. Just ID. You can say that kind of stuff. Sounds smart. Anyway, no, it happens to be correct. You're 100% correct. I don't want to distract you. So you took a log and you summed it up. Okay? Now, we assume that px of theta has this form. Now, I'm going to make the latent variable here discrete. You can do everything that I'm doing here with integrals. It'll feel kind of nice. I like writing those integral signs. It's in the notes that way, but it seems to confuse people on the fly. So I'm going to do it with sums. So just imagine the latent variable is discrete. Okay? Here, this phi is bundling all the parameters. So there really should be a semicolon here. It's all the parameters. Mu's and sigmas, all the ones I forget. Okay? Phi's, they're all bundled somewhere inside that theta. Okay? So let's give a generic algorithm to maximize the likelihood for these latent variable models. And these latent variable models come up all over the place. Okay? Because they basically a way that you assume there's some structure. We assumed clustering. We assumed that they were Gaussian point sources. You now know a whole library of things you can assume about the model. They're all going to be solved the same way. Okay. All right. So let's get to the picture of EM. Ooh, more drawing for me. All right. Let's do it. All right, so here's our function. This is going to be L of theta. Here's the general idea of how we're going to solve this thing. Okay? We are going to start with a guess. Theta 0. This is going to be L of theta 0. Okay. Now, what we're going to do is we're going to figure out some surrogate, which we'll talk about in 1 second, which is going to have a very nice property and is going to come about because of our use of Jensen's inequality, which we're going to call LT of theta. Okay? And this is going to be L0 of theta. It's just called L0 of theta. Okay? Now this function is a function of theta confusingly. So just make sure the notation is kind of written awfully. Let me write this a little bit less awfully. Well, it'll be debatable if it's less awful, but it will be written differently. Okay. So L theta, and the idea here is that it's going to have this curve, L theta, so it's a function of theta, and it's an underestimate of the green curve. Moreover, it meets the original function exactly at theta 0. Okay? So let me write those properties, and I'll give you a time to digest it. It's kind of a weird thing. Now, what's going to be nice about L theta, this character here, is that it's going to be easier to optimize. We're going to optimize it locally. Okay? And so it has this nice concave shape, because it's facing downward. And that's going to let us run a nice estimation procedure, and we're going to be able to find the top of it. And we're going to use that as our next guess. That's going to be theta 1. Okay? Okay. So I'm going to come back to that as I write the property. So L of t of theta is going to always be less than L of theta. Okay? It's a lower bound. And it's tight in the sense that L of t of theta of L of t equals L of theta t. Whoops. Sound good? That's just the picture. All right? Now, when I optimize this character, I'm going to get a new theta 1. This is supposed to be the local max that I just drew. Debatable, but I'm going to claim it is. Then what do I do with theta 1? I do the same process again. I go back up here, I construct a new character, which I'll call L1. Maybe I'll draw it even. I'll use even a different color. Boop. Here. And then I optimize this character. And again I go. Okay? And these are the alternating steps that we're going to do. And our hope, to be really clear, our hope, which right now is nothing more than hope, is that LT of theta is easier somehow to compute argmax. Compute argmax theta LT theta, which is going to be here theta t plus 1, unless I've messed up the notation badly, but you'll correct me. So far, so good? Okay? Now, the E step is given theta t. That is all the parameters, all the cluster sizes, the mu's, the sigmas. It finds L of t theta, which seems like a weird way to think about it now, but it's finding that curve, that likelihood curve, right? So L of t theta, it's the likelihood that given those parameters are relevant. And then the M step, what does it do? It then uses that LT in the other direction, says given L of t, it does this, finds theta t plus 1. And it alternates that, and the picture is, it goes up until it finds something. Now, there's some things you can trust about my picture, and they will hopefully lead you to things. Do you think this algorithm finds a global minimum? Or global maximum, I guess we're doing maximum. No, most certainly not. This is hinted at here. Maybe this character goes way off into the sky, right? But also, you wouldn't expect it to, because when we reduced it to that 0, 1 case, we saw that was a problem for k-mean. So we would expect the same thing should happen here. All right. Now, what we're going to see next time is we're going to come back to exactly this picture, hopefully drawn a little bit better. But here we are where we are. We're going to come back to this on Wednesday, and we're going to start to see the entire derivation for how this algorithm works in terms of this EM framework, and that's going to tell us exactly how it converges. And the story is, I hate to, undersell the lecture so dramatically, is going to be hopefully totally transparent. You do the estimation, then you do what looks like a little bit of a gradient descent or a gradient rule. You fix the parameters back and forth, and you have yourself an estimate. Thanks so much. I'll see you guys on Wednesday.